Okay, from our last video, we were discussing electronegativity. So we'll start right here. We're saying that electronegativity, again, but for our purposes, is the ability of an atom to hold on to its electrons it already has, and let's say acquire additional electrons in the attempt to fill the valence shell, the outermost shell. We said that the only reason an atom primarily would reach out to bond to another atom is to fill its outermost shell. Then if we look at the electronegativity chart, we can kind of get an idea of the strength of atoms as far as electronegativity. Okay. Number one, if an atom already had, let's say, 3 electrons to this outer shell, second energy level, but it needs 8. So would it be more prudent energy-wise to give up those 3 or to try to grab 5? Obviously, it would be easier to give up those 3 because then the shell below that would be filled than to grab 5. So in my chart, as we move across this way, what we can say is we're adding extra electrons. So if I'm oxygen, let's say, for example, right here in this column 6, and that VI says it has 6 electrons. I have 6 electrons, and all I need to do is to add 2 more to have 8. But if I'm over here in, let's say, beryllium, I have 2 in my outer shell, but I need to add 6. So electronegativity increases in this direction, because it would be more energy prudent for you to grab 2 than to give up 6. Now, then I go up this way. Remember that each row adds another energy level. Each row means you're further out from the nucleus with the protons. So the closer you are to the nucleus, the stronger you are to grab additional electrons. So this corner up here, now the inerts here are already filled, so take that out of the equation. So this corner up here is the most highly electronegative, particularly, and when it comes to science, let's say for biology, oxygen, nitrogen, phosphorus, and sulfur are our most electronegative ones. And that kind of goes along when we're talking about obtaining energy and so forth later. So nitrogen, oxygen, phosphorus, and sulfur are highly electronegative right there. And you can study on that. So here again is kind of the electronegativity scale. We won't get too fancy in this course, but all right. So we're looking now at forming compounds, molecules, at least to form molecules. Okay. In this particular, looking at the valence, right here, this hydrogen has 1 in its outer shell. So it's not happy. It'd like to have 2. This oxygen has 6. It would like to have 2 more. So as we look at this, you can kind of glance at that and also read it in the text. Okay. So the inerts, as I mentioned, already have an outer shell filled. As you can see here, their shell is already filled. Ionization energy, we'll say, is the energy to give up electrons. Just like electronegativity was to grab them, we'll say ionization is to give them up. But we won't get heavy off into that. All right. In this, when we look at the chemical bonds, these are the ones we'll kind of just glance at. Okay, an ionic bond. An ionic bond basically forms when 1 or more atoms in a molecule are highly more electronegative than the other. So in this particular case, what will happen is 2 atoms would come together. They could fill the outer shell, but one is highly more electronegative than the other, so it essentially grabs the electron from the other and puts it around its shell. But when it grabs the electrons, it changes the charge. So the atom that grabs the electrons becomes more negative, and the atom that loses the electrons becomes more positive. Thus, there's a opposition of charge that holds them together. A covalent bond is a sharing. What you're doing in the outer shell, you're sharing pairs of electrons. Pairs of electrons. Then we have something we call the hydrogen bond. Okay? We'll go a little further, and then a van der Waals attractive forces we'll just mention. Okay, I want you to read on this. I can't explain it all, but I'll be happy to answer questions if you email me. When one highly electronegative atom with high affinity comes in contact or close to another one, and they can mutually satisfy each other, ionic bond is formed. The reason they call it ionic bond is because both of the atoms now become ions, because remember what an ion was, a charged particle as a result of a change in the electron number. So read through this. The atom of considerably higher electron affinity, or we'll say electron, literally steals the electrons from the other. All right, that's an ionic bond. An example of an ionic bond is sodium chloride. Look at the periodic chart. Sodium chlorine is like in the 7th column. That means it only needs one electron. Highly electronegative, you go to the chart. Sodium is way over in column 1. So if sodium and chloride come together, get close together, chlorine will essentially steal the electron from sodium. Steals an electron from sodium. Thus, chlorine becomes negatively charged, an anion. Its name even changes from chlorine to chloride, and sodium having lost becomes positively charged. So the resultant is, and they're being held together because of this opposition in charge. So look at that in the textbook. Here again is to show you that, how it just literally steals this electron and puts it there. All right. Here again is an example of that. So you'll have to really dig deep and study it, and then email me questions if you have some. All right. So the main criteria for an ionic bond is one or more atoms must be highly more electronegative than the other, and literally pulls the electron from the other, forming a opposition in charge. But when it does that, remember the resultant molecule must have some dimension that's stable in three-dimensional space, or it will fall apart. We go quickly to the covalent bond. The covalent bond is where you share electrons. In other words, to say it another way, one atom is not highly more electronegative than the other. And what will happen, but the two coming together can form a bond, because what would happen is the electrons would float around one for a while and then the other. So a covalent bond is sharing electrons in the valence shell. Remember, sharing. And what it equates to is that one atom is not highly more electronegative than the other, but there is a relationship where it could share. In a covalent bond, the atoms are shared as pairs, and that's not a big situation with you at this level. And in this particular situation, that's where we call it cooperative valence. Sometimes you will share one pair of electrons. That's what we call a single covalent bond. You can share two pairs. That's a double, or even three pairs, and that's what we call a triple covalent bond. And that's the most you can have, a single, double, or triple, and it depends on what is needed. So when I go here would be a single covalent bond. Here's carbon bonding to 4 hydrogens. Carbon right here is 4 in the outer shell. So it could bond to 4 others right here because it needs 4 more. Hydrogen needs 1. So hydrogen would be satisfied with sharing 1 from carbon, each of these, and carbon would be satisfied by doing it this way here. And this would be the structure you would see. Here's a double covalent bond. Oxygen is 6, it needs 2. Another oxygen has 6, it needs 2. So in this case, it's a sharing here, which forms a double covalent bond. So O2, what we breathe, is doing a double covalent bond. In this case, nitrogen has 5, so it would need to do 3. Okay. All right, so please read on this in the text. Here's the comparison of ionic bond to covalent. In this case, you're sharing electrons, and in this case, on the ionic, you literally are stealing them. And the only reason that you don't separate is because now you have this opposition in charge that you would have, negative to positive. The types of covalent bonds, okay? Remember I said that when two atoms come together and neither one is highly more electronegative than the other, but they can bond and satisfy each other, that they would share. Now, here's the situation. Assume that two atoms like oxygen and oxygen come together. They have equal electronegativities, like O2. Therefore, the electrons will equally float around each oxygen the same amount of time. But in a situation where one atom is slightly higher electronegative than the other, slightly higher, but that means not enough to fully pull the electrons away, but slightly higher, then it forms a polar covalent bond, because one side will hold the electrons more often than the other side. The polarity is the side that holds the electrons more often will be more negative because electrons are negative, and the other side will be more positive. The other side will be more positive. That's what we call a polar, because it's having these poles. So here would be a non-polar, equal sharing, like H2. Here, a polar covalent bond, which could be like water. Oxygen is more electronegative than the hydrogens. So in water, the oxygen will hold the electrons longer, thus giving a more partial negative charge. So for example, water, oxygen has more electron affinity, so it holds it longer. Now how long it holds it, how polar is it, is something I just mentioned called the dipole moment. But for sake of this kind of online course, I'm not going to get into that, the degrees of polarity. But that's more of a face-to-face issue for me. Here's oxygen. As I alluded to, oxygen would hold the electrons a little more, giving a more partial negative side, and hydrogen a more partial positive side. So water is a polar covalent molecule. Here again is looking at it, and you can kind of, you have to do a lot of this on your own now. Here's carbon dioxide here, showing kind of the structure. These are what we call formulas here. All right, so to review covalent ionic bonds, an ionic bond, one or more atoms must be highly more electronegative than the other in order to literally pull the electrons. In a covalent bond, that's not the case, but the two can come together, two or more can come together, satisfy the outer shell. Okay? Under the covalent bonds, if it's equal sharing, it's a nonpolar, where both have the same strength. And if it's unequal sharing, we call it a polar covalent bond, exemplified like for water. So here again is a chart you can glance at to see the differences there. Okay, a hydrogen bond is really not a bond, it's a pulsatile force. So what will happen is a covalently bonded molecule, or should I say a hydrogen covalently bonded to one highly electronegative atom, but having an affinity for another one. In that particular case, to give for example, now the hydrogen bond is about 1/20th the strength of a covalent bond. Water sticks together because of these hydrogen bonds. So I will talk about that in the next video. Thank you.